For our last unit here in pre-cal, we're going to introduce you to limits. In order to do that, we're first going to have to review our piecewise functions from earlier this year. We're going to do that because in limits, we'll use piecewise quite a bit. And so remember with the piecewise, it stands for one function being defined by several different functions over a restricted domain. So here, this function is going to be 3x minus 2 when x is less than 1. And it's going to be x plus 3 when x is greater than or equal to 1. And so both of those you should be able to graph because that's a line and so is this. They're both written in the y equals mx plus b form. There's a couple of different ways you can go about this. So here we've got a y-intercept of -2 and then a slope of 3. So this is going to go up 3 units and to the right 1 and up 3 to the right 1. Or you can see that as going down 3 and to the right 1. I'm sorry, to the left 1. Now this is going to be true for where x is less than 1. So that means everything to the left of this 1 right here. And so what you want to do is get rid of all of the parts that are to the right. So that value right there is no good. And this one's actually not valid either because that is x is less than 1. It would be an open circle there. So you graph as many points as you need to do that. And the graph stops there since it's when it's less than 1. And I'm going to use a straight edge here to graph the line. So that's one way is to graph the entire line and then erase the part that you don't want. Or the other way is to actually look at it, only graph the values that you need. In this case, you would start at 3 here. Now I know I don't need that because it says x is greater than or equal to 1. Then I use a slope of 1 to go up 1 to the right 1. And that would be my first point since that is at the x value of 1. Then I use my slope of up 1, right 1. And so this is the part of the graph that we care about. So that right there is the graph of our piecewise. The next thing we would want to do is answer some questions here. F of -1. And if you remember, f of x is what goes there. And so what this is saying is that when x is -1, what is our function value? So -1 would happen on this first one. So you can plug in -1 here, or you can look at the graph. At -1, our function is at -5. At 0, it is at -2. And when x is 1, it is at 4. I use the 4, not this 1, because this is an open circle. There's not actually a point there. The 4 is the one that's a closed circle. That's where our point is. All right, here is another one, and I'll practice that one again. So this one defines it over 3 different ones. X is less than 1, x is equal to 1, and x is greater than 1. So I'm going to start with the x is less than 1 right here, and here is my line. I start at -3, and then I use my slope of -2 to go down 2 and to the right 1. That puts us at 1, so I'm going to do an open circle right there. And then I would use up 2 and to the left 1 for that slope of 2. I'm sorry, -2. And so again, I would use a straight edge to connect my dots there. And so there's the first piece of my piecewise. Now at 1, it says it is 1, so that's going to be this point right here. So my x value is 1, my y value is also 1. And then this last part says we have this quadratic x minus 3 squared plus 3 when it is greater than 1. Now with quadratics, this is in the transformational form. So remember it went to the right 3 and up 3 from the parent function. Or you can think about the vertex 3, 3. So I go to 3, 3. There's my vertex. And for a quadratic, it goes to the right 1 and up 1, and the same thing on the other side since it's symmetrical. The next value would go over 2 and up 4, and also symmetrical, but that puts us at the 1, so that would be an open circle since there's not an equal sign right there. We go ahead and connect our dots, and so there is that piecewise. For f of -1, it is at -1. At 0, it is at -3. And at +1, it is 1. So you should be able to get those values for our function as well. All right, so we said we're going to look at these piecewise functions and determine our limits, since that's what we're introducing today. So let's go to that part. That was our quick little review to get us started. It says the limit of a function deals with what happens to the y value of a function as you get close to an x value. We don't necessarily care what happens at the point. We just want to know what happens as it gets close. So let that sink in. The limit is what is happening as it's getting close to that point, not what's happening at that point exactly. All right, the notation for limits looks like this. And so you read that as the limit of f of x as x approaches c is this number, L. And its meaning is as x gets real close to the value of c, so as x is approaching, it's getting really close to the c value, not necessarily at the c value, it's just getting really close. F of x gets real close to this L value. The value of the function at c, or f of c, may or may not exist. So the f of c may or may not exist. In some examples, we'll use a calculator table or a graph to find the values of the following ones. So we're going to start by looking at these here. And you can use a calculator or you can remember what it looks like either way. So we'll start going that way. When I say looking at the calculator, you're just going to the y equals and putting that in to look at the graph itself. So the limit as x approaches 4 of 3x squared. You should recognize this as a quadratic. And so our quadratics look like this. All right, so there is our quadratic. Our quadratic is continuous. That means I don't have to pick up my pencil to draw this. It is on every single one of these points here. And so it wants to know as x approaches 4. Well, 4 would go this way. As we're moving to the right, where is our y value going? In this case, since it is continuous, I can actually just plug that 4 in for x. Since it is on my graph, this graph is continuous. And so we get 3 times 16, which is 48. That would be our limit. As x approaches 4, y is approaching 48. So as we get closer to 4, y is getting closer to 48. All right, for this next one, we have a line. And so its y-intercept would be 3 right there, and it's got a slope of 1. So we've got a graph that looks like this. Again, this is continuous. I probably should have wrote that on that top one. You want to make sure that you understand. When it's continuous, you can just plug it in. That's going to help you find the point because that's what it's moving towards, whatever that y value is. And so we get 3 plus 3, which is 6. All right. This you should recognize as a rational. And so rationals can take on a couple different graphs. If I simplified this, I would get x plus 3 times x minus 3 over x minus 3. So we factored this difference of squares to look like this. Well, that x minus 3 and that x minus 3 cancel, and we have x plus 3. So if we looked at this graph, x plus 3 looks exactly like we just did here. But we know when we cancel, we end up with a hole. So the graph there has a hole. Now, as my x gets really close to that 3, it is getting close to that point right there. So again, we can plug it into that x plus 3. So I get 3 plus 3 is equal to 6. That would be the limit there as well. This point is undefined, but my graph is getting closer and closer to that point. And remember, we don't care about what's happening exactly at that point. We care about what is happening as it approaches that point. All right. So now let's talk about some graphs. That's the easiest way to see the limits is by doing those graphs. So the ones we just looked at, you could put into the y equals, or you can sketch the graph. Here they're giving you the graph and they're asking you for the limit. And so it says f of -1. Well, if I go here, f of -1 is this point right here at -2. Now that can be our limit or it cannot be our limit. It depends. So we look at the graph and we think about our limit as it approaches -1. Well, as I'm getting closer and closer to this -1 on the x, it is getting closer and closer to this point right here, which is 2, -2. And so that is the limit. In this case, they're both the same. All right. F of 3, however, in this one is undefined. There's a hole there. So this is undefined. Now the limit as x is approaching that 3 is defined because this graph is getting closer and closer to 2, which is our value right here. So the limit is 2. Again, we don't necessarily care what's happening at the point, we care what's happening around it. And so it is getting closer and closer to 2. And so that would be our limit there. All right, this next one's a little bit strange. It's got this hole, but the point is down here. So when we find f of 3, it is defined at 3. It's -2 right there. Now, when we think about the limit, though, it is not -2. We care about what's happening on our graph here. And as it's getting really, really close to it, it is getting closer and closer to 2. So the limit would be 2. F of 3 is -2 because that's exactly what's happening at 3. But what's happening around 3 is that it's getting closer and closer to 2. All right, this next example here has f of 1. At f of 1, it is 2 right here. So it is defined there at f of 1 to be 2. Now, if we think about the limit though here, this does not have a limit. It has a jump discontinuity here. And so it is not getting closer and closer to one particular point. From this side of the graph, it's getting close to 0. And from this side of the graph, it's getting closer to 2. So there's no limit on this one. We write that as DNE, does not exist. So looking at these examples before we move on to the next ones, I want to show you that they can be the same. F of -1 and the limit can be exactly the same. The f can be undefined and the limit can be defined, or the f can be defined and the limit can be undefined, or they can be different values. So there's not one particular way of doing it. You really need to think about what's going on as it gets closer and closer to that point. All right, so there's a few more examples that we're going to look at. So f of 3 in this particular case is at -1. This again, though, would be a DNE. It is getting closer and closer to this point on this side and this one on this side. So this would be a DNE. Now, when they don't give you a graph, again, you can use the calculator to find a graph. In number 9, we're going to have to use our calculator here to find our value. So let's practice that. Alpha y equals allows me to put in a fraction. And so I'm going to put in this fraction the way I see it here. And so I've got x raised to the 3rd power minus 2x squared plus 4x minus 8. And then in my denominator, I'm going to have x raised to the 4th power minus 2x raised to the 3rd power plus x minus 2. All right. When I hit graph on this, I'm going to let the calculator take its time here. We've got a couple things going on with this graph. We have an asymptote, it looks like right here on this rational. So we've got an asymptote on our graph right here. We've got this piece and then we've got this piece. Now the part that we care about is what it's approaching, because they can ask you different parts of this graph. In this case, they're asking us for x is approaching 2. Well, 2's right here. So I can see it's approaching right there. So the easiest thing to do is try and plug it in to see if we can find what that value is. Now, when I do that, I get 2 cubed minus 2 times 2 squared plus 4 times 2 minus 8 all over 2 to the 4th minus 2 to the 3rd power plus 2 minus 2. Well, this turns out to be 0 in the denominator. So this is undefined. So that didn't help me plug it in. That means that there has to be a hole there. So we don't really see it because it's a little bit zoomed out, but that tells me that there's a hole there since we don't see an asymptote and we don't really see a jump on here. So I can use my graph to do it by hitting trace and then getting closer and closer to that 2 value. So there it is at 0.806. If I hit zoom and I zoom in, I'm going to be able to see that point to get it even closer. Again, we want to move to that cursor closer and closer to 2 because we care about what it is approaching at that point. And so right here, I can get closer to that 2. And that gives us 0.85 right there. I can continue to get even closer by hitting zoom in and zoom closer and closer. Another way of doing that is by looking at the table. So if I go to my table set here and I want to go to 2 and I change this to 0.1, that's going to get me closer to that 2 value. So when I go to the table, I see that it says error at 2. And we knew that because it was undefined there since it was divided by 0. But here our values are not exactly the same. And we are trying to figure out what it's getting closer and closer to. So now I go back to my table set and I move this to 0.01. I go back to my table. Oops, I want to make sure I started at 2 because I want to be as close to that point as possible. Now they're a little bit closer together, the 0.88 and 0.89. Well, we said this limit is as it gets really, 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 really close to this. So I can go back to my table and I can get even closer than 0.01. I'm going to go ahead and do it to 0.0001. Now when I go to the table, I can see it's 0.889 and 0.8888 here. So all of these values are 0.8, repeating really, which is 8/9. So that would be my limit as x approaches 2. It is getting closer and closer to that 8/9. All right, for our next one here, we've got the limit as x approaches 0 of the absolute value of x over x. Now I can already see if I plugged in 0 here, it'd be undefined. So that's not really going to help me. So I'm going to put this into the calculator to see what it shows me. Still have that weird window. Sorry, let me zoom out so you can see that better. See, here is our window. So this graph right here, I know it's not at 0, so that's got to be an open circle. Looks like this. That is not approaching one particular number. This side is approaching -1, and this one is approaching +1. So here again would be a D and E. It's not approaching one number. It's not getting closer and closer to that. Here it was getting closer and closer to this 0.8, so that's the limit. Here it's not getting closer and closer to 1 point. Now this next one's kind of interesting. So this is 1 over x squared. That's one of the parent functions we talked about. So I don't need to really put it in my calculator because you should know it looks like this. In this case, there is an asymptote at 0. And it's asking us as x approaches 0, what is our limit? Well, since it is getting closer and closer to 0, and we know that's undefined there, so f of 0 is undefined. That doesn't necessarily mean we don't have a limit. This right here is moving up forever. It's following that asymptote all the way up forever. So the limit to this would be infinity because it's going up forever. All right, to wrap up our lesson now, we're going to talk about a couple more examples and just a little bit more notation just to make sure that you guys have it. So on these next 4 graphs, we're going to look at the situations again, the different situations you're going to come across. So this one right here, this is a continuous graph. These are really going to be our easiest ones, are going to be those continuous graphs because they're flowing towards a number on both sides there. You can tell that number is what it's getting closer and closer to. So our f of 3 is 2 and our limit is also 2. That's the point it's getting really close to. The next one is looking like this. It's got a hole in the graph. So in order to graph this, I would have to jump over this point and keep going. So this is not continuous. This is one you will not be able to plug in the number necessarily from the original equation because it's going to give you an undefined point at that point. But in this case, so f of 5 is undefined. So the limit is not going to match this. As it gets closer and closer to that 5, it is getting closer and closer to 1 here as a function. On both sides, we can see that. So our limit is 1. For this next one, we've got this line here. It's got the hole and then it jumps over here. This too is considered not continuous because we have to jump over that point. I would have to lift my pencil in order to graph it. At f of 5, it is defined. It's defined right there at 1. But that is not our limit. Our function is getting closer and closer to 3. From both sides here, it is getting closer and closer to this point 3, so that would be the limit. So again, these two will not be the same. When it's continuous, easy, they're both the same. All right, on this next one, we have a jump discontinuity. So this one again is not continuous. And these are the ones we really need to think about. So I want to point out some notation on this that we put there. Right here next to the 3, you see a plus on the top. That means coming from the right. That's what that little plus means. On this side, we have a minus. That means it's coming from the left because minus on the x-axis is the left and plus is on the right. And so that helps us come up with a limit. If both of those are the same, then it's got a limit. If they are not, then it does not have a limit. So at f of 3 here, our graph is getting closer and closer, or sorry, at f of 3, our graph is at 4. Now, when we come in from the right, so as I'm going this way from the right-hand side, it is getting closer and closer to that point right there, 4. From the left, though, as I'm coming in from the left, it is getting closer and closer to 2. Now, when we talk about the limit, it has to be going closer and closer to both points. In this case, our limit does not exist because they're not moving towards the same point. As we move closer and closer to that 3, we are not getting closer and closer to a particular point. All right, so the bottom line on most functions is that if the function is continuous and you can substitute the number into the function, do it. That's the easiest way. The output is your answer. So something like this, the limit is of 7, well, that's easy. All of the points are at 7. Same thing with this one. This one is a line. A line is continuous, so the easiest way is to plug in that 3, so we get 7 there. A quadratic is continuous, so we can plug in the 3 there. 3 squared is 9 times 5 is 45. This negative 5x, again, we have a line, so we can plug that in. Right here, this one looks tricky because it looks like a rational, but that's really just 1/2 x. So we can plug that in. We get the 6 here, and that gives us 3. This right here, this is a quartic. It's raised to the 4th power. That is continuous. It's a polynomial. So we can plug in the 2 right there. We plug in the 2 for all of those, and we get 10. The cosine curve. That is continuous. Remember, we graphed that. It was that up and down, and it is continuous. So I can plug that in. The cosine of pi is -1. Again, same curve. The cosine of pi over 4 is √2/2. So any graph that is continuous, plug it in. That's the easiest way to find the limit. Now, if you plug in the value of the x and you get 0/0 or infinity over infinity or negative infinity over negative infinity, then you either look at the graph as we did previously. So you want to look at these graphs to see what's coming out for that undefined value. Or we're going to talk about some more techniques next time. So come back for our second video here and I'll show you some more techniques on finding those limits. That was your introduction.